Hello, and welcome to the FlowRy Show, a journey through life's tapestry, wisdom for every generation. On this show, we talk about where generations intertwine, sharing stories, insights, and dreams. Whether you are a seasoned sage or a curious young mind, we're all students in the grand classroom of life. Here with me today is my co host, Mike Ryan, and a very special guest. I'm your host, Nicole Flowers. As we explore a tapestry woven with threads of collaboration, dreams, and lessons learned along the way, today we're going to dig in and just start peeling back what do we mean by quantum implications and looking at this from a multi-generational perspective. Delving into this profound topic, as I've indicated, we have a special guest, Dr. Michael Hehenberger, who is a renowned expert in life sciences. He has done research and development as well as previously leading business development at IBM Research. He applied innovative technologies to tackle industry challenges. Michael holds advanced degrees in physics and quantum chemistry. And today he's going to share his expertise that spans computational chemistry across various life science topics. But for today, we're going to dig in around quantum computing. Michael, welcome, and thanks for being here with us.
Well, thank you, Nicole and Mike. Let me just add that as you hear from my accent, my Arnold accent, I was born in Austria, and I studied physics in Vienna. And there I was first introduced into topics that are relevant for quantum computing, or what our topic today. So I learned mathematics, statistical mechanics, superconductivity, quantum mechanics, and I was intrigued by that, and I thought I would continue studying, and I took my PhD in quantum chemistry then in Sweden. So I went to Uppsala, Sweden, and my teacher, Professor Lövdin, was a renowned, really a top expert in this area. This is why I went there, and he also had started a quantum 3 project at the University of Florida, so I spent time there as well.
Well, thank you.
Let me just a little more, because I just want to tell you why I'm so fascinated by this topic, and I almost spent my whole career in preparing for this. So quantum chemistry involves a lot of computer programming. So the electronic structure of atoms, molecules, and the solid state, they can be calculated by solving the Schrödinger equation. And Schrödinger was an Austrian physicist who discovered quantum theory in the 1920s, independently along with Heisenberg and Dirac. But his version, called wave mechanics, which is based on the theory of differential equations, turned out to be the most useful and suitable for electronic computers. So I became a heavy user of supercomputers, being a quantum chemist, probably the heaviest user at our university, in particular computers made by IBM. And after my years in academia, it was quite easy for me to transition then to join IBM. And then many quantum chemists had found a home in IBM, mostly in the Almadin lab in San Jose, California. And IBM research there was responsible for many important inventions and early Silicon Valley breakthroughs, like the first programming language, the first disk drive for storing data, the first relational database, and so on. And I worked in several IBM locations, first in Sweden, then in Paris, in San Jose, and finally in New York. This took me here. So that's my background.
Quite extraordinary. I'll jump in just for a second, in that the closest I picked up there, Michael, is that you mentioned Heisenberg, and I'm often mistaken for Heisenberg in the Breaking Bad series, but that's not me. That's the closest I come. But it's an extraordinary journey you've had, and not just in quantum chemistry, but quantum computing. And then if you add the complexity of your academics, as well as your multicultural background in multiple, Paris and the like, and U.S. and beautiful Austria. It's a wonderful journey. So we're very excited to kind of scratch the surface.
I've been an immigrant twice. I was first an immigrant in Sweden, and then I'm an immigrant here.
So wonderful.
I know what it is to kind of adapt to another culture.
Yeah, well, as you mentioned, Arnold may bring us the brawn, but you have definitely brought us the brain. So we little brains and brawn. So we thank you on behalf of a grateful nation.
Don't underestimate Arnold.
Yeah, never. I mean, he was my governor. I am in California, so okay. I have a lot of respect for Arnold. So with that, Nicole, you want to?
Yeah, absolutely. So Michael, it is believed that quantum computing stands to revolutionize information processing. Scientists and research analysts, they believe that quantum computing will be tackling problems that intrinsically for classical computers, it's going to be far more vast. Imagine a future where complex simulations for drug discovery are performed in minutes and not years. And we also have this topic around quantum cryptography, which offers the possibility of this unbreakable encryption. Tell us today, just simplify for our viewers, what is quantum computing in its most basic form?
Well, it's really a step up from classic computing, and it is based on a very different concept, because classic computing is based on the bit, which can be 0 or 1, and that's pretty easy to understand. And then you build on that, and of course we had many years on doing that, and have come a long way. But the quantum computing qubit is a very different thing. It is a two-dimensional Hilbert space. Hilbert space is the space we're dealing with in quantum theory. Hilbert was a professor in Göttingen, where everybody went. It was kind of the center of the universe in mathematics and quantum theory in the 1920s and 30s. And so you have the concept of basis vectors, and the notation that's used in quantum computing is actually the one that was invented by Dirac. It's called Bra-Ket. So you have a ket 0 and a ket 1, and the difference between a qubit and a bit is that the vector, the wave function, the psi, which is usually a Greek psi, that wave function is defined as alpha times ket 0 plus beta times ket 1. And alpha and beta are complex numbers. And they have the squares of those numbers, alpha squared and beta squared, the sum of those have to add up to 1. So the wave function is on a circle that has radius 1, a sphere of radius 1.
So in other words,
so that is a very different concept, and you really need to dig into some basic quantum theory to understand it.
Right.
Absolutely. So in other words, quantum computing is leveraging the principles of superposition and entanglement.
Yes, and entanglement was actually I already referred to my favorite Austrian scientist Schrödinger, who coined that term, entanglement.
Absolutely.
So it's one of those concepts in quantum theory that are sometimes counterintuitive in the classical world, but actually they shouldn't be, because what happens in the quantum world can easily also happen outside. But let me just go through a few concepts. The first is the role of the observer. So if you do a physics, any experiment in the quantum world, in the microscopic world of electrons and photons and atoms and molecules, if you are in the very small dimensions and you do something, you measure something, you're actually changing what you measure. So the observer has an influence on the result. And that is something you cannot get. It's unavoidable in quantum theory. The other thing is entanglement. We have this concept in chemistry. We have in a simple atom like helium, you have a closed shell, and you have an alpha electron and a beta electron. There are only 2 electrons in helium. And if alpha and beta are the spin up and spin down of the electron. And when you have an electron that spin up, the other one in the same shell must be down. So that means those properties of spin up and spin down are entangled. If you measure one, you know the other one is a different one. So that is the concept of entanglement. And it's also true for photons and other properties. And that is very important in quantum computing. Because everything is kind of entangled. And first, when you measure something, the wave function collapses into a state that can then be examined, and then you have a result of a calculation.
And simply
there's one more thing that's really important, and that is, Schrödinger called it wave mechanics. And so particles and waves are equivalent. So you have a dualism. The photon can be a particle, it can also be a wave. And those two are equally valid. When Einstein did his first photoelectric experiment, he got the Nobel Prize for that, actually, not relativity, he got it for that. He proved that a photon can be a particle. But it is, of course, also light is a wave. So, and that is true for all elementary particles, electrons as well.
So in very basic terms, quantum computers can perform computations exponentially faster than classical computers for specific problem sets. So
yes, definitely yes.
Michael, tell our viewers, how do you envision quantum computing revolutionizing the way we process information? What's your perspective on how information will be processed using quantum computing technology?
Well, when we talk about processing information, we talk about number crunching, doing something with numbers and getting a result, and also accessing information from databases and kind of trying to find something. And in both areas, there are special algorithms that have been developed that show that quantum computers that are based on the qubit instead of the bit are orders of magnitude faster. Like there's the algorithm that shows that factoring can be done much faster. There was a mathematician at Bell Labs, Peter Shor, who demonstrated that. And then there was another mathematician actually also working at Bell Labs. Those are those were the major industrial research labs, the Bell Labs and IBM Research. And unfortunately, the Bell Labs no longer exist in that form, so that is gone. But the history remains. And right. Grover had developed this algorithm for finding, say, a phone number in a big phone book. The problem is you have a phone book of 1 million pages, and you try to find a number. Grover's algorithm lets you do that quadratically more faster than in a classic computer. It is really based on that concept of qubits. So you have, instead of, as in classical computing, you have to examine 500,000 pages as you would have to do in a classical computer. If you have 1 million, you have to examine 500,000 on the average.
Right.
What Grover's algorithm does, you only have to look at 1,000 instead of to look at 1 million, to find a number in 1 million. You only looked at 1,000 pages, because the pages are taken by the computer such that you can use quantum wave functions, quantum wave properties like interference. You know, in waves you have interference, and you can have that, and you use those properties to have things cancel out, and that property of waves is then used to reduce the work you have to do to find a particular phone number in a phone book quadratically more faster, and that's a huge advantage. You can look at problems. Some problems, they are impossible to solve, but with algorithms that are specially developed for quantum computers, you have a chance of solving them.
So I would imagine early adoption of quantum technologies is likely to occur in sectors such as finance, healthcare, material science, just driven by the potential for significant advancements. What industries do you think will be the earliest adopters of quantum information technologies?
Well, when you say industries, if you include also universities, the academia, that's probably always comes first, and also government research.
Yeah.
But in terms of real industries, commercial companies, it would be the biopharmaceutical industry, because we will be able to speed up life sciences research, drug discovery, also what I call clinical decision intelligence, to assist the doctors in diagnosing patients and finding the best possible treatment for the patient. Those things will dramatically be impacted by quantum computing. But you have to also understand that the fact that I just described, Grover's algorithm, that you can go into a 1 million phone book, it means that you can also look at databases and access information and process that information, and you can, by doing so, really improve artificial intelligence. You can go into machine learning and do that much faster. So you talk about quantum machine learning that will dramatically accelerate artificial intelligence. So there is definitely a joint development that impacts both, and those are the kind of two great important new developments in technology. It's AI and quantum computing, and I think AI is a little ahead, but quantum computing is going to influence AI in a big way.
Yeah, I jump in as far, because you touched upon drug development. I know you have some expertise in that. I've got more of a involvement in it, in that I know, some having gone through it, we've involved with some drugs that are developed and now are on the marketplace, which can be hit and miss on the clinical trials, right? But it typically, my understanding, takes about 10 to 15 years to get a drug to market from, let's say, coming out of the university, that then goes to a private sector and then raise capital and the like, and it goes through a cadence of FDA approvals through trials that take sometimes 20 people, then 100 or whatever. But what I think that what you're saying, if I understand correctly, instead of taking 15 years and having a smaller sample size, you could actually increase the sample size and the cost that's involved with that, right? So the cost of those 15-year journey for drug development, I've heard is as low as $5 billion, as high as $80 billion, real cost involved. So if you're able to take AI and quantum computing, that you're able to reduce the time of getting a drug to develop, you have more data that hopefully it's not going to fail in the clinical trials and who you have do the clinical trials. And then lastly, the cost of doing that hopefully isn't, $5 to $80 billion. Do you think that's reasonable?
I think the greatest impact will be in drug discovery, but clinical trials, you still have to deal with patients and you cannot just simulate everything. I think the speed up is not as significant as maybe in drug discovery, but still, as long as you deal with data, massive amounts of data, you will have a speed up.
Yeah, and the other point that you touched upon was, I think you call it clinical assessment or clinical helping the doctor, the physician, or whoever the caregiver is, that suddenly has, I used to run hospitals, and you have the massive amount of data that, is in the world and not necessarily helping the doctor make a clinical decision, right? I know, many personal mentees of mine or whatever that took 9 or 10 different years of getting something as simple, not as simple, but as something as Lyme disease that was miscalculated or misdiagnosed or whatever. So I'm hopeful that quantum computing and, some things you talk about are able to help the clinician, make the evaluation first. And so it goes back to patient care. So you're able to expedite that and get the treatment that's necessary.
Yeah, I think the quality of diagnosis and treatment recommendations will improve. There's no question. But you still need the doctor to make the final decision. I think it's more like assisting the doctor to do something, unless you have let's not talk about too much about that future. But other industries, I would like to just mention other industries there. You've talked about financial modeling, cybersecurity. There's also something like, it was an interesting project by Microsoft. It's not only IBM, Microsoft, Google, there are others heavily involved in this. Right. Microsoft has a quantum computing project, and they did an interesting thing with routing traffic. So they did a study, and when you're using Google Maps and you are using Android Auto or Apple, whatever system you're using in driving, the recommendation you will get in finding your way in a congested city is going to be kind of very selfish. So you are going to do the best thing for yourself. But if you say you have 5,000 people who get the same recommendation, then that's not optimal.
Right.
Because you will compete with all those others.
Right.
So what Microsoft did in Seattle is that they looked at this situation with 5,000 with quantum computing. How could you possibly get the optimal outcome for the 5,000? Not just everybody gets the same, but you get a different recommendation. So that is one possible application area.
Yeah, I know that, I've been using Waze, that, Google acquired, but my wife and I are driving down the road and we'll go, off a highway or whatever, because there may be an accident on a highway. And we say, oh, it looks like everyone's following Waze, right? So that kind of goes to your point.
That's the issue, yes.
Right.
So. It's good for you, but if everybody does the same, it's no longer good.
Right. You're definitely not optimizing for yourself, right?
Yeah.
So,
in other areas is you already mentioned chemical materials research. So, for instance, developing better batteries for electric cars and things like that. So that's definitely going to be impacted by quantum computing.
Yeah, I mean, I live in San Francisco, and I have for the past 5 or 6 years or more, I've been watching autonomous vehicles, whether it's Tesla, whether it's Waymo, which is the Google, or whether it's Cruise, which is GM and others, that they're constantly, trying to improve that. And now they're actually open where you can, a driverless car, right? And some of them, Tesla's removing the steering wheel, but I would imagine you need big data to make sure you don't have future crashes. and that makes a lot of sense as far as a practical use in our daily lives.
Yeah.
And, Michael, we want our viewers to know that we do not envision that we're just going to go directly to quantum computing. There'll be an interim period where there'll be a hybrid systems where we'll
Yes.
combine classical computers and now integrating or introducing quantum computing to leverage the strengths of both approaches to continue solving very complex problems and more efficiently. To your point around the drug discovery and in other areas, especially when we start looking at quantum AI for areas like natural languaging, processing, etc. But wanted to just highlight for our audience, as we continue down the path of artificial intelligence, at some point we envision that quantum machine learning will begin to advance artificial intelligence, although you have also indicated that AI is already ahead of its curve. But once as we start integrating quantum computing with AI, we foresee that we'll be able to enable far more vast analysis of larger data sets, to Mike's point and to your point, or development on drug discovery and other applications will have more accurate predictive models. Any final thoughts from that perspective?
Yeah, I fully agree with you. It's going to happen, and the hybrid point was a very good one. So not every problem is suited for the quantum computing, and you have to decide which part of the problem are you going to let run on the conventional computing, which one will benefit from the quantum computer. So the hybrid approach is also something that, for instance, IBM is now teaching. IBM has a toolkit for quantum computing, and they call it QuizKit, and they're teaching it, and it allows you to separate the problem and use both to your advantage. And that is also a way of getting faster into that new environment. So you don't have to wait until everything is quantum. You can mix and match and make sure that you're doing the best possible preparation for the future.
Dr. Hehenberger, Michael, we want to thank you. Today, you've discussed with our viewers the concept of quantum computing and its potential to revolutionize information processing by simply leveraging the principles of superposition and entanglement. Unlike classical bits, which can be either 0 or 1, qubits, as you've introduced and defined for us, can exist in a superposition of both states simultaneously. We want to thank you for sharing and simplifying for our viewers the concept of quantum computing. As we always say on this show, we're sharing stories to create a bridge between generations. It allows us to connect on a much deeper level, learn from each other's experiences, and foster understanding. Embrace the power of storytelling to build meaningful relationships and create a more connected world across the generations. Thank you for joining us today on the FlowRy Show. Until next time, we'll look forward to having you again. And Michael, thank you so much.
Thank you, Michael. It's been very.
Thank you.
Hopefully there won't be a test on it later, but I'll try to pass.
Well, maybe next time we can talk about consciousness.
Yes, and in fact, just to tee it up for our viewers that this is just one of a few other conversations that we're planning to have with Michael. And yes, Michael, to your point, I think talking about quantum consciousness, just what is the between the realm of quantum realm and our perception of reality, I think it's going to be a very intriguing topic for us to dig into, and it's quite profound for a lot of.
I'll just add, although I have not read them, we have talked before about Michael's books. If you want to mention them, especially when it has to do what we can learn from animals, right? And look up Michael's name on Amazon, and I think he has some very insightful discussions as far as what we can learn from different animal species going forward. So thank you.
Actually, I have a new version of that book coming out in the middle of December.
Wonderful.
called in the shadow of animals.
Well, it's perfect for holiday giving, Michael.
I hope it's going to come out in time. Yes, for
Okay.
that.
Well, next year then, right?
But
Thank you.
I do want to share with our viewers that Michael had recently updated his paper on quantum information. So I'll definitely be sharing that once we are off screen, so our viewers
Yes.
will be able
Yes.
to read that.
Please provide a link. It's I think it's now really up to date because this field is moving so fast,
Right.
That it's difficult to keep up with all the things going on. And it's IBM, it's Microsoft, it's Google. There are some other players. There are universities not only in the United States. There are things going on in Europe. There are things going on in China. We have a lot to talk about in the next 5 or 10 years.
Yeah, it's been a quantum leap of discovery. So we thank you again.
Okay.
Thank you so much, Michael. Okay, until then, everyone, so long. Have a wonderful day. Bye-bye.
Thank you. Bye.
Bye-bye.